Welcome back to our course in trigonometry. As you might have guessed from the video where we had the overview, at least in the first part we're going to be dealing with triangles quite a lot. And one of the main facts that we are going to lean on, at least some of the time, is the Pythagorean Theorem. Now I'm sure you probably know it already, so I'm not going to belabor the point here, but I would like us to understand, one, why it's true, not just that it's true, but why it's true, and two, try to get a feel for how somebody might come up with an idea like this. So this is my little sketch of a tile floor. I want you to imagine we're looking down at a tile floor. Okay, now all the tiles are big squares. Now, of course, all the squares can be cut along the diagonal. Okay, so each of these is also two right triangles here. Okay, so we've got a little 90-degree angle there. All right. Now on the legs of my right triangle are squares. Okay, so I'm going to use a couple of different colors here to shade these in. So maybe I'll shade this one in that kind of pinkish color, and this one I'll do in the blue. Okay, so on the legs of the right triangle we have these squares. That's a little annoying. Let's turn that off. Okay, so we have these squares. Now we can also make a big square on the longest side or hypotenuse of the triangle by doing this. Okay, so on the hypotenuse we have a big square. But of course, each of these shaded squares can be cut in half as well into these triangles. So you notice we could take this blue square and fill it in here and here. And we could take the pink one and fill that in here and here. So this big square on the longest side is equal to the sum of the area of the two squares on the legs. Okay, so the Pythagorean theorem is a generalization of that to all right triangles, not necessarily ones where the two legs are equal. Okay, so let's just, so that we have it in our notes, so that we have it in our video, let's kind of write out what it is here. So if we have a right triangle, A, B, C, where angle C is right. Now this is a convention that we're going to be following the entire course. Capital letters will denote angles. So if I talk about capital A, I'm talking about angle A. Now the convention we'll follow is angle A opens up onto side A. So side little a is opposite angle A. So angles will have capital letters, side lengths will have lowercase letters. Angle B opens up onto side B, and angle C, in this case the 90-degree angle, opens up onto side C. So if I have a right triangle with side lengths A, B, and C, then A squared plus B squared equals C squared, generalizing what we saw right here. The area of the squares on each of the legs total up to the area of the square on the hypotenuse. Okay, so I'm sure you've seen it before. It'll be a very useful theorem. I'm going to pull a problem from the book that we'll be using in our course. So, okay, I had one picked out. Let's do this one. Okay, so in triangle ABC, with C equals 90 degrees, so angle C is 90 degrees. Let's work one where we have this. Let's say if A equals 2 and C equals 6, find B. Okay, so in triangle ABC with C equal 90 degrees, A equals 2, C equals 6, we are charged with finding B. Okay, let me make a little picture here. Angle A opens up onto side A. C is the 90-degree angle. I'll put that down here. So B is over here, opposite angle B. So we're given in the problem, A is length 2, C is length 6. Okay, now, by the Pythagorean theorem, we know a relationship that the side lengths fit into. The sum of the squares of the lengths on the leg is equal to the square of the hypotenuse. Okay, now B is our unknown here. So I know that 2 squared plus my unknown B squared should be equal to 6 squared. Okay, so we can perform these calculations pretty easily. Of course, we remember squaring. It means you take whatever the base is, multiply that number by itself. So 2 squared means 2 times 2, so that's 4. 6 squared means 6 times itself. 6 times 6 is 36. Okay, so if this equation up here is true, we can solve it and get that B squared has to be 32. All right? Now, that doesn't tell me B just yet. It tells me B squared, so I have to work backwards. B squared equals 32, and let me go up here and give myself a little more space. Okay. So if B squared equals 32, then B would be equal to whatever the square root of 32 is. Okay, so that's how we work backwards from the result of squaring. We take the square root. So squaring and square roots are inverse processes of each other. They undo each other. All right, now let me make a little note here about simplifying square roots. Okay, square roots behave very nicely with respect to multiplication. In other words, the square root of a product is equal to the product of the square roots. That comes from rules for exponents. Okay, now, when you're simplifying a square root like this, what you want to do is think of the largest perfect square that divides into this number evenly. In this case, it happens to be 16. Sometimes you can't simplify it. If there are no perfect square divisors, we'll just leave it as it is. But in this case, 32 does have a divisor that is a perfect square. And when I say perfect square, I mean square of an integer. So 1, 4, 9, 16, 25, 36, 49. Those are our squares. Okay? So this can be broken up. It's the square root of 16 times the square root of 2. So 4 radical 2. All right, so given this information about our right triangle, so we know A, we know C, we found B. All right, so the Pythagorean theorem gives us this nice relationship between the squares of the side lengths, and the key idea, the thing to take away, is that if we got a right triangle and we know any 2 of the side lengths, then we can always figure out the other side length. Okay, so a very important relationship. We're going to use it a lot throughout our course in trigonometry.